Hello there and welcome back to this video series on control systems. In the previous video, we have considered mechanical systems with spring, mass and damper and saw how to derive the transfer function of such systems. We have written individual equations for spring, damper and mass from the first principles, and then we saw how to combine them into a single equation and then derive transfer function. We'll continue the discussion and consider one example in this video. We may consider other examples during tutorials. We'll see how to write the equations and derive transfer function of a simple SMD system. For that, let us consider a spring mass damper system that is shown here. Okay, you have a spring K1 connected to a mass which is connected to a spring and damper. Very carefully you can see and very clearly you can see that this spring K2 and the damper B2, they are in parallel. But what remains to be seen is whether this M is in parallel with K2 and B2 or whether it is in series. Similarly, whether the spring K1 is in series or whether it is in parallel with M, that is what we need to carefully see. It is a good idea to carefully do such analysis and see which elements are in series, which elements are in parallel. So we'll first identify that and clearly represent the system showing which elements are in series, which elements are in parallel, and then go on to derive the transfer function from Ft to Xt, from Ft to Yt, and thus from Xt to Yt. When we say transfer function from Ft to Xt, we mean capital X of S divided by capital F of S. Similarly, when you say from Ft to Yt, it is capital Y of S by capital F of S. Similarly, this would mean capital Y of S divided by capital X of S. If you carefully notice, the force at one end of the spring F of T is the same as the force at the other end of the spring. That is, force at A is equal to force at B. Okay, because the same force is going through the spring K1 and M are in series. That is what we noted here. The force at end B, ends A and B of spring K1 is the same. That force is going to M also. That is, F is going through K1 and F is going to M. So the spring K1 and M are in series. However, you can note something surprising regarding M, K2 and B2. It can be very clearly seen that this K2 and B2 are in parallel because the force is shared amongst them. Some part of the force goes to K2, some part of the force goes to this B2. However, you can see that the force that is coming from this point B, some part of it is used up in accelerating this mass, and only the remaining force goes to this parallel combination. That is, this force F is split in three ways. One, a force that is used in a component of force that is used in accelerating M, another is going to spring force K2, another going to damper B2. So this M, K2 and B2 are in parallel, they are not in series. So we note here that the mass M, spring K2 and damper B2 are in parallel. We need to show the mass somewhere here. Thus we note that K1 is in series with MKB2. MKB2 forms one group which are in parallel, and the spring K1 is in series with that. So this we note as something like this. We redraw the picture as something like this. M, K2 and B2 are in parallel, which is in series with the spring. Let me animate it once again. Okay, this is the system, and actually what we should be drawing is this. Okay, M is in parallel and then K1 is in series with this whole arrangement. With this noted, we can very easily write the equations and find the transfer function. We have seen that each M contributes ms square, each damper contributes bs, each spring contributes K2. K, that is the net impedance of these three put together is ms square plus b2s plus K2, because these three are in parallel. If these are in parallel, they simply add up. So you can see that this net impedance of these three, which we represent by Z1, is in series with the spring K1. So the net impedance may be written by reciprocal of this K1 plus reciprocal of this Z1, the whole reciprocal. That is, take reciprocal of sum of reciprocals of K1 and Z1. That's what exactly we have written. The total impedance ZE may be obtained by putting Z1 and K1 in series. Okay, thus we obtain this as ZE as something shown over here, and the relation between f and x is measured as f of t is ZE multiplied by x of t, and f of s is ZE of s multiplied by x of s. You may want to carefully note, when we are trying to find the transfer function between f of t and x, we are considering all the elements that are between the point where x of t is measured and the ground. This hatchings here, this hatching here, this hatching here, this hatching here, they all indicate ground, that is the fixed point. When we try to find relation between f of t and x of t, consider all the elements between this line and the ground, that is the spring K1, M, K2 and B2. That is the reason why we found ZE here. So we have seen that relation between f of s and x of s may be written as f of s is ZE multiplied by x of s. So this transfer function between from f of s to x of s is written as shown here. We refer to this as equation 1. Remember, this equation 1 gives xs by fs. We have seen that the force F acts at end A, the same force is transmitted to end B also. So to find the transfer function between f of t and y of s, we can just get rid of the spring, because the force is acting here and displacement is occurring at a point neighboring the force. So we redraw this diagram as shown here in this picture and find the net impedance between y of t and ground. Between y of t and ground is ms square plus bs, b2s plus k2. That we have noted here. Okay. Since the same force acts at A and B, the diagram is drawn here, and the equation between f of s and y of s is given in equation 2. F of s is z1 multiplied by y of s. So g2 is transfer function from f to y is given as here. Now you can carefully look at equation 1 and 2. Y of s divided by f of s, and equation 1 has x of s divided by f of s. F of s is common, so we can very easily see that the transfer function from x of s to y of s may be found by dividing one by the other, which is g2 by g1 as shown here. So equations 1, 2 and 3 characterize the dynamic behavior of the system under a exciting force f of t. With that, we may give summary of this video as shown here. Transfer function of SMD may be derived by carefully examining the elements in series and elements in parallel. Each mass contributes a ms square impedance. Each damper contributes a bs term. Each spring contributes a term k. Correspondingly, when they are in series, you sum the reciprocals and take the reciprocal of that. If they are in parallel, you will just sum them. to find the effective impedance and write the transfer function. The assembly system is a second order system because S square term is appearing in there. I think that's all we have for now. Have a great day.